Imagine this. You're trying to find, that one specific detail in your personal notes, or maybe you want an AI assistant to help make sense of your emails. The idea sounds great, right? But then you get that little worry. Is all my private stuff being sent off somewhere? What if you could have really powerful AI, but it works right there on your phone or your laptop, totally offline, totally private? Okay, let's unpack this because today we're diving into something pretty significant from Google, EmbeddingGemma. It's a new open source model, and it's basically designed to put serious AI power right onto your own devices and, crucially, keep your data. Well, yours.
Yeah, and what's really fascinating, I think, is that embedding Gemma isn't just, another small step forward. It kind of signals a real shift in the AI world. We're moving towards thinking about performance per watt as a really key metric. It's not just making things smaller, it's rethinking how we design these things, which could honestly open up totally new types of devices we haven't even thought of yet. It's really about empowering you with smart apps right on your device.
Okay, so our mission for this deep dive is to really explore embedding Gemma from all sides.
Yeah.
We'll look at what it is, how it pulls off what it does, why it's such a potential game changer for privacy and this whole on-device AI idea, and of course, how it stacks up against the competition out there. By the end, you should have a pretty clear picture of where things might be heading for intelligent apps, the kind you carry around every day. That vision, AI, just sitting there in your pocket, ready to help. It's compelling. So to really get how that's even possible, let's peel back the layers. What is embedding Gemma fundamentally?
Right. So at its heart, it's a text embedding model from Google. It has about 308 million parameters, and it's multilingual. It's built using the Gemma 3 architecture as a base that's the same foundation behind some of the bigger Gemini models you might have heard of.
Yeah.
But the key thing here is how it's been specifically engineered for efficiency. It's aimed squarely at on-device and edge AI. This means it can handle pretty sophisticated tasks like Retrieval-Augmented Generation RG, basically finding info and generating answer from it, and semantic search too, all running locally on your own hardware.
And the efficiency part is probably what catches people off guard, right? It sounds like it needs huge servers, but you're saying
Yeah.
it can run on my laptop, my phone.
Absolutely. That's the real aha moment, I think. Its efficiency is kind of staggering. This model can run using less than 200 megabytes of memory, especially when it's quantized. Maybe we should quickly explain quantization. It's basically a compression technique. You take the model's internal numbers, which are usually high precision, like floating point numbers, and you convert them to lower precision integers. This makes the model much smaller and faster, often without losing much performance. And that low resource need is what makes it feasible for, your smartphone, your tablet, your laptop. We're talking AI that used to need a whole data center, now potentially fitting in your pocket.
That's genuinely remarkable. Shrinking AI down like that, it feels like a real breakthrough. What were the sort of architectural tricks or decisions that made this possible without sacrificing too much power?
Well, it starts with that Gemma 3 backbone we mentioned. Using that existing proven architecture is just smart R&D. They're leveraging work they've already done. They take that strong foundation, and then they cleverly adapt it for this specific embedding task.
I'm really curious about that adaptation. How do you take a model built to predict the next word, like a generative model does, and turn it into something that understands the whole chunk of text? What's the magic there?
Yeah, that's a really neat part. It involves switching the attention mechanism. Generative models typically use causal attention. Each word or token can only see the words that came before it. It looks backward. But for embeddings, you need the model to grasp the full context, right? The whole sentence, the whole paragraph. So they switch to bi-directional attention. This lets every token see every other token in the input, forwards and backwards. This allows it to build a much richer, more holistic numerical representation that's the vector, or embedding of the entire text. That's absolutely critical for getting high-quality embeddings where similar meanings end up close together in the vector space. The research even hints they use something called T5 Gemma initialization, suggesting they borrowed ideas from the T5 models, which are known for being really good at text-to-text tasks, to give it a better starting point.
Okay, so it's not just predicting anymore, it's really understanding the whole context. And the 308 million parameters, how are they structured to keep it so lean?
Good question. About 100 million parameters are for the core transformer layers, the processing engine, if you like. And around 200 million are for the token embedding vocabulary, basically. It's understanding of words across many languages. This kind of distribution, focusing a lot on language breadth but keeping the core processing tight, helps make it compact yet multilingual. Combine that lean design with the quantization-aware training, meaning it was trained knowing it would likely be compressed later, and that's how you hit that sub-200 millibeat target. It's built for efficiency from the get-go.
I've also heard this term, Matryoshka Representation Learning, MRL. Sounds fancy. What's that about?
MRL is actually a really cool practical feature. Matryoshka, like the Russian nesting dolls, right? It lets a single model output embeddings of different sizes, different dimensions, without needing any retraining. So its standard output is a detailed 768-dimensional vector that gives you the best quality. But developers can just chop that down, truncate it to smaller sizes like 512, 256, or even 128 dimensions. And the model is trained so that even these smaller vectors are still effective. They're renormalized. This is super useful for the edge world, where devices have vastly different capabilities. You don't have to pick just one size. MRL gives you a toolkit to adapt. Powerful laptop, use 768. Simple device, maybe 256 is enough.
That flexibility sounds incredibly useful, but does choosing the dimension add complexity? Like, how do you know if 256 is good enough versus 768? Is there a typical trade-off?
Yeah, that's a fair point. It does mean developers need to do a bit of testing for their specific use case. Generally, you'd start with the highest dimension your target device can comfortably handle for the best accuracy. But if you're hitting memory or speed limits, you try truncating down. You test 512, then 256. Even 128 dimensions can sometimes be surprisingly effective for simpler tasks. And the memory saving is huge. It's about finding that sweet spot between performance and resource use for your application.
Got it. So you find the right fit. What about other tech specs? Context length, things like that?
It can handle input sequences up to 2048 tokens long. That's generally plenty for most retrieval tasks, like searching through paragraphs or medium-like documents. And smartly, it uses the exact same tokenizer. The thing that breaks text into pieces the model understands is the bigger Gemma 3 generative models.
Yep.
This is quite clever because if you're building one of those RAG systems on a device, using EmbeddingGemma for retrieval and Gemma 3 model for generation, you only need to load one tokenizer into memory, saving precious resources. Oh, and the training, done on Google's TPU v5e hardware, their latest AI chips.
Okay, architecture and specs make sense, but a model's only as smart as its training data, right? And this thing apparently learned from a huge amount, 320 billion tokens. Tell us about that data set.
Huge is right. And it's not just big, it's diverse and carefully put together. There are three main parts. First, masses of web documents from all over the web in over 100 languages. That's where it gets its broad linguistic understanding, its multilingual power. Second, they specifically included code and technical documents. This teaches it structured patterns, specialized terms, makes it good for code search or technical Q&A. And third, this is really important, lots of synthetic and task-specific data. This means millions of carefully crafted query document pairs. The model wasn't just learning language, it was explicitly trained to be good at retrieval, to make the embedding of a question end up mathematically close to the embedding of its correct answer. That direct training is key for its performance.
When you're playing with that much data, especially web data, responsible AI becomes absolutely critical. How did they approach that?
Hugely important, yes. Google emphasizes this with the Gemma models. While the model architecture is open, that curated dataset is proprietary. It's a major asset they don't just release. They talk about rigorous filtering, multi-stage filtering to remove harmful content, like CSAM obviously, but also automated filtering to try and strip out personally identifiable information and other sensitive data. It's about trying to make these models safer and more reliable for broad use, though no system is perfect, of course.
Okay, so it's built efficiently, trained extensively. Let's talk performance. How does it actually measure up when benchmarked?
The standard way to test these is using benchmarks like MTEB, the Massive Text Embedding Benchmark, and its multilingual version, MMTEB. These are pretty exhaustive tests. They cover different tasks, retrieval, classification, clustering, summarization, about 8 categories in total. Uses 58 different data sets across 112 languages. We're talking the latest version, so it's rigorous testing.
And Google's big claim is that at release, EmbeddingGemma was the top-performing open multilingual embedding model under 500 million parameters on MTB. That sounds pretty strong for its size class.
It is a strong claim, and the numbers seem to back it up, at least for that specific point in time and category. Looking at the 768-dimension version on MTD Multilingual V2, it scored 61.15. For English only, V2 68.36. And for Code V1, it got 68.76. That 61.15 on the multilingual test is particularly noteworthy for a model this compact. It shows it really does handle many languages effectively. So yeah, those scores do validate that best-in-class for its size claim, particularly the multilingual and code performance stand out.
accuracy is one thing, but for on-device, speed and efficiency are just as vital. What do the metrics say there?
Right. Speed-wise, they report inference latency under 15 milliseconds for a typical 256 token input. That's fast enough for real-time apps like quick searches. And memory, as we said, under 200 millib RAM, especially with quantization.
So you really do get that efficiency without a massive hit to performance. That seems like the holy grail for on-device AI.
Pretty much, yeah. That's the key takeaway. The sources show that even a quantized version like Q80 still scores around 60.93 on MTEB multilingual. That's incredibly close to the full 61.15 of the uncompressed model. You lose very little accuracy for a big gain in efficiency. And this focus on performance per watt, it's strategic, right? It signals that the best AI isn't always the biggest anymore. It's often about what runs optimally on the hardware you actually have. It kind of democratizes powerful AI, moving it beyond just the cloud.
Okay, this is where it gets really practical, the flagship use case. The thing this really unlocks. You mentioned on-device RGI.
Exactly. On-device, private, offline retrieval-augmented generation. This is the big one. Think about all the personal data on your phone or laptop notes, emails, documents, maybe even messages. Building an AI assistant that could understand and use that usually meant setting it all to the cloud. Big privacy concern for many. EmbeddingGemma lets you potentially do the whole RA process locally. 2 stages. First, retrieval. You ask a question. EmbeddingGemma turns your question into an embedding. It then searches a local index of embeddings made for your documents, finds the most relevant bits. Second, generation. Those relevant snippets plus your original question get fed into a local generative model, maybe a small Gemma 3 variant, which then writes an answer for you.
And the killer feature there is privacy and offline use.
Precisely. Your sensitive personal data never has to leave your device. It enables that dream of a truly personal AI that acts like a second brain, organizing and accessing your information, but with complete privacy. And it works even if you don't have an internet connection. They even showed a proof-of-concept browser extension, using it for doing real-time local search across the web pages you visited. It's like having your own secure mini search engine.
That's powerful stuff. Beyond RGAG, what else could you use these efficient embeddings for on a device?
Oh, lots of things. The embeddings are high quality. So, semantic similarity, finding things with similar meanings. Good for recommendation engines or finding duplicate files or notes. Classification, things like sentiment analysis, is this review positive or negative, or spam detection. Clustering, grouping similar documents together automatically. Useful for organizing research papers, customer feedback, whatever.
Now, for developers wanting to actually build with this, I heard prompt engineering is really important. It's not just plug and play.
Yeah, that's a key detail, yes. You don't just feed it raw text. The model was trained to expect specific prefixes, or prompts, depending on the task. Using the right prompt helps the model generate the most effective type of embedding for that specific task. So for a search query, you'd format it like task dot, search result query, your actual query. For indexing a document to be searched, it's title, text, document content. There are specific formats for fact verification, code retrieval, sentence similarity too. Using these is crucial to get the best results. It leverages how the model was trained.
Okay, good tip. And how easy is it for developers to get their hands on it and start playing around?
Very easy. Google's made it widely available. You can find it on Hugging Face, Kaggle, and their own Vertex AI platform. The recommended way to use it is often through the Sentence Transformers library. It's super popular and integrates well with frameworks like LangChain and Llama Index, which people use for building RAG systems. And it supports different ways to run it. Proper production serving, running it right in a web browser using transformers.js or local inference tools like Llama, they clearly want people to use it.
Right. It's not operating in a vacuum, though. How does EmbeddingGemma actually stack up against some of the other strong, compact embedding models out there?
Good point. The competition is fierce in this space. Let's compare it to, say, Nomic Embed Text v1.5. Nomic's model is smaller, around 137 million parameters. Performance is in a similar ballpark, and it also uses MRL, that variable dimension feature. Nomic's main advantages are a much longer context length, 892 tokens, versus EmbeddingGemma's 2048, which is great for really long documents. And it's multimodal. It can handle text-to-image search too. But EmbeddingGemma's big plus is its massive multilingual training across 100-plus languages. So the choice really depends, right? Need long context or images in English? Maybe Nomic. Need broad language support. EmbeddingGemma looks stronger there.
Okay, what about BAAI's bridge base on v1.5? That one's popular too, known for being efficient.
Yeah, BGE base is another strong contender. Very efficient and only 110 million parameters. And it scores really well on English MTB, around 63.55. Its strengths are Maybe it's simplicity. The latest version doesn't strictly need those task prompts for good performance, and it's tight focus on English retrieval performance. But again, embedding Gemma wins on the built-in multilingual side and has that MRL flexibility. It just highlights that the market's fragmenting. There isn't one best small model for everything. They're optimizing for different things. Context length, languages, ease of use.
And looking at Google's own portfolio, it seems like they have a clear two-pronged approach with embedding Gemma and their big cloud-based Gemini embedding API.
Absolutely. It's a very clear strategy. Embedding Gemma is the open, lightweight, on-device, privacy-focused option. It's for developers, for the edge, for offline use. The Gemini embedding API is the opposite. Proprietary, much larger, cloud-only, aiming for the absolute state-of-the-art performance for big server-side applications. This lets Google play in both sandboxes. They fostered the open-source community and on-device innovation with embedding Gemma, while also serving high-end enterprise needs with the Gemini API. And like we touched on, it really points towards a future of hybrid AI systems.
Okay, but no model is perfect. Even with all its strengths, what are some of the inherent limitations people should be aware of with embedding Gemma?
For sure, limitations exist. First, training data bias. It learned from 320 billion tokens of web data, code, etc. That data inevitably contains biases, which the model will reflect. Developers need to test for and potentially mitigate these biases. Second, language nuance. Like most models today, it can struggle with complex stuff like sarcasm, humor, or very figurative language. Third, domain specificity. While good generally for highly specialized fields, think deep legal analysis or complex medical texts, it might need fine-tuning to match the performance of larger models specifically trained on that domain. It's a great baseline, but maybe not the final answer out of the box for hyper-niche tasks. And finally, that context length. 2048 tokens is decent, but some competitors offer more, which matters if you need to process very long single documents.
And ethically, especially around privacy, what's the key takeaway?
The key thing is responsibility. Google designed embedding Gemma for on-device privacy, which is great. But the application developer using the model is ultimately responsible for ensuring their app complies with privacy laws and ethical standards. Just because the model can run locally doesn't automatically make every application built with it perfectly private or ethical. Developers need to be diligent about how they handle user data within their specific app.
So stepping back and looking at the bigger picture, what does a model like embedding Gemma really signify for where AI is heading?
I think it's a really strong signal. It represents the rise of edge AI, bringing powerful computation away from centralized clouds and closer to the user. It genuinely enables a new category of privacy-first applications. Think truly personal assistants that know you but keep your secrets, or offline search that just works anywhere. And that dual strategy with the Gemini API points to this likely hybrid future we mentioned. Systems might intelligently decide, okay, this quick task needs privacy. Use the local embedding Gemma. This needs deep analysis and I have connectivity. Okay, maybe ping the cloud model. It's about bringing intelligence closer, making it more personal, more accessible.
So wrapping up, what does this all really mean for you, the listener? Embedding Gemma feels like it genuinely redraws the map for what's possible with AI on your own devices. It's taking capabilities that used to live in huge data centers and putting them right there in your personal space with privacy designed in from the start.
Yeah, it's a foundational piece for this next wave of personal AI. If you're a developer thinking about private RAG systems, it's a fantastic tool. If you're a researcher, it's a solid baseline for fine-tuning on specific data. And even if you're just curious about where AI is going, it shows this incredible trend towards powerful, flexible, yet efficient models designed for your hardware. Quick recommendations: mobile web devs. Leverage it for privacy-first features. Use MRL for adapting to different devices. RAG builders. Go for on-device pipelines, but really pay attention to those task-specific prompts for best results. Researchers. Great starting point for domain specialization.
Which leaves us with a final thought to ponder. With models like embedding Gemma making private, on-device intelligence increasingly real, how might you change your relationship with AI knowing your data can genuinely, finally, stay your own?